This is a quick video, I hope, about the evolution of this little automated bilge pump system I've been trying to build for my boat for over a year now. It's pretty simple. I started out with this doofangle with relays. So you have a float switch up here, water rises, float switch triggers, turn pump on. And the trick is I don't want the pump to turn off right away because I don't want it to chitter if the water level goes up and down. So I want it to turn on for about 30 seconds. So this is the first iteration using relays. Basically the float switch triggers this relay, which charges up this cap bank with an adjustable resistor. And then when the float switch turns off, relay turns off, but the other relay over here will stay on this cap bank until this discharges, which will then turn this off. This is very dumb. Let me get less dumb, because we needed a huge cap bank, 166 millifarads about, and that's actually right here. That was that first prototype with 2 relays. Very pretty cap bank though. Totally didn't work though. This is actually how the schematic looks. These are all for balancing the capacitors so they don't untune over time as capacitors will. And yeah, less dumb, use a BJT and an amplifier, because before you needed actually all the energy of the caps to power or to energize this relay, because the relays are super lame. They look like a 1K resistor when they're getting turned on, which is a lot. So this BJT only needs a 10K resistor for input impedance. So use the BJT, much smaller capacitor, everything gets better. And then I evolved to one switch. The whole thing could get my goals, which I thought was pretty funny. Just an RC float switch charges up the capacitor of the MOSFET on the gate, and then it just discharges, which is ridiculously simple. And if you wanted to make it a little fancier, you could use a MOSFET driver, which is what I went with, which is this doofangle in here. That thing barely fit in here before, but now it's a little rushed, but it's down there. And then I have some diodes just so I can't flip the reverse the polarity. The MOSFET's down there. This hits the top of the lid so it kind of sticks all together. There's the driver in there. Very simple, very nice. Not too bad. And then, I have a switch, a fuse. All right, so here's the test. We have our power, or 12 volts coming in. And then we have this simulates our pump. It's right now tuned to pull about 600 milliamps. It's a little tunable DC load I made with a MOSFET on the gate of another MOSFET with a pot on its gate. Anyways, so now we can move the float switch. Funny thing about this whole thing is I somehow inverted the float switch, so I have to fix that. You'll see. So here, we'll push the float switch down and let's see what happens. So say we fill up the bilge, boom, see? Pump turns on, and then water level drops. And then if we wait about 30 seconds, and any second now, boom, turns off. So that's pretty cool. It was 30 seconds, I paused the video. So what's going on here is when this float switch triggers for even a second, it charges up this cap, which is above the threshold turn on voltage for this MOSFET driver, which outputs either a 1 or a 0. So either a high rail, which is about 13 volts, or 0. And if it's 13 volts on the gate of an min-MOS turns into like a short circuit. And then this is our load right here, which is represented by inductor. So, I actually need to put the diode in right here. I haven't done that yet. I need to do that. So that's for back EMF stuff. But anyhow, yeah, so as this capacitor discharges through this resistor at a rate of RC, so that's the capacitance times the resistance, 63% discharge in voltage within one time constant. The VIN on this, the VIN threshold, is actually much lower than 63%. It's like 5 volts or 2 volts. So I actually can get 3 or 4 or 5 time constants out of this. I had a larger cap, but I had to take it off until you pass that threshold, and then this guy turns off. The only problem is there could be some chittering as we pass over the threshold, but this is still better than this because as this passes down, the MOSFET will be basically tuned to perfectly match the impedance of the battery and the load and everything, and we'll have maximum power drop through the MOSFET at one point. Whereas at least in this way, yeah, there's chittering, but hypothetically the MOSFET is a little better off. So, very cool. I hope you guys enjoyed this. I might have posted something about that before, but just goes to show with a little bit of time you can get a lot better at stuff. This was August of 2023, and this was summer, and then today, or like last week, I was like, huh, wait, this does the exact same of this. 10 times less components. Anyways, I hope you enjoy. Have a good time.